Hello students, welcome back. In this part, we are going to discuss about the number of atoms belongs to one particular unit cell. So here the unit cells we have considered are only cubic unit cells, and we will also discuss about the various types of unit cells possible for different types of crystal classes as well. So let's start the presentation. Now we are going to discuss about primitive unit cells. We already discussed about the types of unit cell in our previous part. Now we are going to discuss about the primitive unit cells. So how many types of primitive unit cells we have, and what are the characteristics of these these unit cells. Okay. So the various types of unit cells possible for different crystals are, you can see in this picture where I am showing 7 types of unit cells. Okay. So these 7 types of primitive unit cells are possible. They are namely cubic, tetragonal, orthorhombic, hexagonal, rhombohedral, monoclinic and triclinic. So we have 7 types of primitive unit cells. So you can see all these 7 types have different unit cell characteristics, parameters. So if you take cubic, it has the 3 edge lengths equal and all the angles, the edge angles are equal to 90. Okay. But if you come to tetragonal, there is a difference. There is a difference from cubic, and orthorhombic is different from these two. Okay. So these are differing in edge lengths or also edge angles. Okay. So let's discuss more about it. Here you can see the 7 crystal classes we have: cubic, tetragonal, orthorhombic, hexagonal, rhombohedral, monoclinic and triclinic. So total we have 7 primitive unit cells. We can remember them by like this: CTO, HTMT. CTO, HTMT. You can memorize like this from top to bottom: CTO, HTMT. Okay. So C means cubic and T means tetragonal, etc. So till we have triclinic. So these are having different unit cell parameters. So if I take edge lengths, the cubic is having all 3 edges equal, and the tetragonal is having 2 edge lengths equal, and 1 edge length is differing from the 2. Okay. So A and B are equal, but they are not equal to C. And orthorhombic, we have all the 3 edge lengths differ. All the 3 edge lengths are different. Okay. So if you see from top to bottom, only 2 crystal class have all the edge lengths equal. One is cubic and other is rhombohedral. Only these 2 are having all the edge lengths equal. So you can remember it like this. So cubic is having A equal to B equal to C, and cubic, and other is rhombohedral is having rhombohedral or trigonal. Okay. It is also having all the 3 edge lengths equal, A equal to B equal to C. But in all other in other 5 cases, the edge lengths, all edge lengths are not equal, and if you take the 3 crystal systems, orthorhombic, monoclinic and triclinic, we have all the edge lengths different. So orthorhombic, A not equal to B not equal to C, and monoclinic and triclinic, which are the last 2, they are also having different edge lengths, A not equal to B not equal to C. Okay. So we have covered 5, only 2 are remain. So those 2 are having same unit cell parameters, A equal to B not equal to C. So in this way, somehow you are able to remember these edge lengths. Okay. So if you do it by general means, like if you generally try to memorize it, soon after 2 or 3 days you will definitely forget this. You will be confused. You will get confused. But if you remember like this, it will be somewhat easy, and even you can remember them for a long time. Okay. The similar thing you can do for angles also. So luckily these 3 are having say 90-degree angles, Okay, so you can just write it here, all the 3 are equal to 90, but in all 4 cases the scenario is different. The trigonal, in trigonal case, all the 3 are equal, but they are not equal to 90, right? So you can also see the other angles also. Okay, and here possible types of unit cells for each crystal class. So for cubic, we have a primitive cubic, we have a body centered, and we have a face centered. So 3 unit cells are possible. So here 2 unit cells are possible, and we discuss only about the cubic. So all other unit cells are not so important to us. Okay, only the hexagonal is important to us, but cubic and hexagonal are important unit cells that we need to that we are going to learn in this chapter. But all other unit cells are not, they're not important. Okay, and also given some examples for each crystal class. Okay, so this is about the types of primitive unit cells and the unit cell parameters. So let's study further. Yeah, this is a very, very important concept. So number of atoms in a unit cell. I want to calculate the number of atoms in any particular unit cell. How can I calculate? Okay, that's the question that I am having in my mind right now. So how can I approach? So if you see, if I consider any crystal lattice, it is containing a number of unit cells, huge number of unit cell it is having. So you can see, if I take one particular unit cell, say suppose if I take a primitive unit cell, which is a simple unit cell, and it is having the particles at the corners, right? It is having the particles at the corners. So it is having 8 particles. But what you need to understand here is, the 8 particles are not only belonging to this unit cell that I am considering, but these 8 particles are also belonging to other surrounding unit cells. This is the point that you need to observe. So it's not like that if one particle is at the corner of one unit cell, then it is entirely belonging to only that unit cell. No, it is shared by other unit cells. So I'll tell you like how the atoms are shared. Okay, so if I consider, we know that particles are present at corners, they are also present at the face centers, they are present at the body center, they are also present at edge centers. Okay, so there are 4 different positions the particle can have. Okay, so if you see, this is the particle that is present at the corner, okay. So this particle is not belonging to one unit cell, but this is equally shared by 8 unit cells. Okay, I hope that you are able to observe this. So this particle is shared by 1 unit cell, 2, 3, 4. So 4 at the bottom and 4 at the top, 5, 6, 7, 8. So this is equally shared by 8 unit cells, and 4 at the bottom and 4 at the top, right? So how much of this particle belongs to one particular unit cell? One particle belongs to 8, so only 1/8 part is belonging to one particular unit cell. So its contribution to one particular unit cell is 1/8. So this is what you need to understand. 1/8 means that particle is equally shared by 8 unit cells, and only 1/8 part belongs to one particular unit cell. So 1/8 is belonging to this one, and 1/8 is belonging to this one. So similarly, all 8 are sharing this one particular, right? So 1/8 is the contribution of a particle to one particular unit cell, which is present at the corner. Okay, so this is done. So let's come to the particle which is present at the face center. So if you see, if a particle is present at the face center, this face is shared by 2 unit cells, right? So the particle is also shared by 2 unit cells. So only half of the particle is belonging to each unit cell. So the contribution of a particle which is present at the face to one particular unit cell is only 1 by 2. Okay. So, this is 1 by 2. So, if a particle present at the body center, if it is present at the body center, then that particle is entirely belonging to that unit cell. Okay. Since it is not shared by any other unit cell, it is only belongs to one unit cell. So, at the body center, a particle is going to have a contribution 1. Okay. So, what about at the edge centered? Edge centered. So, if a particle is present at the center of edge, then what is the contribution of a particle towards one particular unit cell? That is 1 by 4. How it is 1 by 4? Because each edge is shared by 4 unit cells, right? So, each edge is shared by 4 unit cells. So, if a particle is present at the edge center, say suppose here at the center of this edge, only 1 by 4th will belongs to one particular unit cell. Okay. So, this is the contributions of the particles. So, let us calculate the number of atoms in each unit cell one by one. Okay. So, let us first calculate the number of atoms in a simple cubic unit cell. So, we know that the simple cubic unit cell is nothing but a primitive cubic unit cell has atoms only at its corners, only at the corners it has, and each atom at the corner is shared between 8 adjacent unit cells. So, therefore, only 1 by 8th of an atom or an ion actually belongs to particular unit cell. So, I want to calculate how many it has, how many atoms it is going to have. So, this particle has 1 by 8th of this particle belongs to this unit cell. So, total I have 8 particles. So, 1 by 8 into 8 is equals to 1, right. So, this 8 is, I have 8 particles at the corners, and 1 by 8 is contribution of one particle towards this unit cell. So, total as a whole I have only one particle present in the simple cubic unit cell. Okay. So, number of atoms present in a simple cubic unit cell is 1. So, let us go to number of atoms present in an FCC unit cell. We know that in FCC unit cell, the particles present at the corners and they are also present at the face centers. Okay. So, let us calculate the total number of atoms. So, we have 8 atoms. So, 8 corner atoms into 1 by 8th atom per unit cell. So, 1 atom. So, this is from the corners, and from the face centers we have 6 face center atoms into only half of each face center atoms belongs to this unit cell. So, into half you will get 3 atoms. So, total we have 1 plus 3, 4 atoms. Only total 4 atoms will belongs to in FCC unit cell. Okay. So, FCC unit cell has 4 atoms. The number of atoms present in it is only 4. And if you come to BCC, which is even simple, because it has at corners. So, from corners there will be 1, and from body center there will be 1. So, total we have 2 atoms, 1 atom from the corners, 1 atom from the body center. So, total we have 2 atoms. Okay. So, effectively only 2 atoms belongs to a BCC unit cell. Okay. So, this is about the number of atoms in FCC, BCC and a simple cubic. Okay. So, let us solve some questions based on the concept that we discussed right now. Potassium crystallizes in a body centered cubic lattice BCC. What is the approximate number of unit cells in 4 grams of potassium? Atomic mass of potassium is given. So, we need to calculate the approximate number of unit cells. Options are given A, B, C, D. So, how to approach this question? How we can solve this question? Here it is given that 4 grams of potassium we have taken. So, mass of potassium we have taken is 4 grams and its molecular mass is 39. So, from this we can calculate the number of moles, right? That is mass by molecular mass 4 by 39. This is the number of mole, right? So we know that 1 mole contains 6.023 into 10 power 23 number of Avogadro number of potassium atoms, right? So 1 mole contains Avogadro number of atoms. So 4 by 39 mole contains how many? How many? That is simply 4 by 39 into Avogadro number of atoms. So the number of atoms, the potassium atoms present in 4 grams of potassium is these many, okay? But it is given that the potassium is crystallized in a BCC cubic lattice. BCC cubic lattice. So each BCC unit cell contains 2 potassium atoms. That we discussed right now, that number of atoms present in BCC is 2. So each BCC unit cell contains, so one BCC unit cell is containing 2 potassium atoms. So how many unit cells are going to contain 4 by 39 into Avogadro number of potassium atoms? Okay. So how you can calculate this one? This is simply 2 atoms are present in 1 unit cell. So these many atoms are present in how many unit cells? That is simply 4 by 39 into Na divided by 2. Okay. So it is 2 2s are. So it is 2 by 39 into Na. This is the number of unit cells we have. So Na is 6. Instead of Na, you can substitute the value 6.023 into 10 power 23. So if you calculate this value, you will get approximately the number of unit cells are 3.09 into 10 power 22. Okay. So this is how you need to solve the question. First calculate the number of moles. From that calculate the first number of moles, calculate. From that calculate the number of potassium atoms, From the number of atoms calculate the number of unit cells. Okay. So this is how you can solve this question. So let's move to the next question. Okay. An ionic compound made up of atoms A and B has face-centered cubic arrangement in which atoms of A are at the corners and atoms B are at face centers. So if one of the atoms is missing from the corner, what is the simplest formula of the compound? Options are given. So how can you calculate this one? It is also not a big question. It is also an easy question. So there are 2 atoms we have. One is A, other is B, and here A is present at the corners. So at corners you can have 8 atoms. So each one is contribution 1 by 8. So effectively one atom of A will be present in the unit cell, and B is at the face centers. So B is at the face centers means the number of atoms of B is equals to what? 6 into 1 by 2, that is equals to 3. So A is 1, B is 3. So it is AB3 will be the formula. But it is given that if one of the atoms is missing from the corner, so out of 8 atoms, now there are only 7 atoms at the corners, right? So now we need to calculate the formula, the simplest formula. So we have 7 atoms. So each atom is having a contribution 1 by 8 into 7. So total there are 7 by 8 atoms of A is present, and the number of atoms of B remain unchanged. So there are 3 atoms of B. So the formula will be A 7 by 8, B 3. But it should not be a fraction, it should be an integer. So you can multiply with 8, right? So it will become A7, B24. A7, B24, option A is the right answer. Okay. So in this way you can calculate the simplest formula of the compound. Okay. While studying this chapter, if you get any doubts, you can post it for free on askIITians.com. How? First open the website, and if you see at the top right, you will see a discussion board. So simply click on that. It will take you to the next screen. Yeah. In the next screen, you will see the Ask Experts, a separate section on the right hand side. So select a relevant category for your question and simply post your question here. We experts at askIITians will provide answers to your questions within 24 to 48 hours. So students, in this part, we discussed about the different types of unit cells possible for various crystal systems. And we also calculated the number of atoms present in simple cubic, body centered as well as face centered cubic unit cells. So now we are moving into the very interesting zone of solid state, that is the packing of atoms in a solid. So if I have given you a set of spheres and I ask you to arrange these spheres in 3 dimensions, so in how many ways you can do that? So to know more about the packing in solids, keep watching for my next part.